Okay, this is going to be the lecture over chapter 14, the slides. It's going to be a little bit more in depth than going through the key points, but I think it is definitely worthwhile to kind of see what is new and happening and how this can affect our lives. And by that, I mean electron beam therapy. You can see here, you've got an electron beam coming in, striking a piece of gold. And you can see all of the different tracks and whatnot that these electron or, whatever is released out of that. So kind of neat stuff. Some of the things that I covered in the key points will also be covered here. There are going to be some things here that I want you to pay attention to that are going to be very, very important. In the clinic, you're going to end up using electrons with a range somewhere between 6 and 20 MeV. They're going to be used to treat superficial tumors, less than 5 cm in depth. And one of the main reasons you do that is that you've got a sharp drop off in dose beyond that tumor. In other words, they're not going to penetrate that far. They're not like photons where you're going to see, a considerable, not a great amount of exit dose, but you will see significantly less of that with electrons than you will with photons. The advantages of electrons, particularly over brachytherapy or tangential photons or superficial X-rays, is going to be the dose uniformity and the target volume. You will have a little bit better of that. It's a stronger beam. And you'll have minimal doses to deeper tissues. So you can kind of get the best of both worlds over these modalities. A lot of skin cancers are going to be treated with electrons. Lip cancers, of course, falls into that same category. Chest wall irradiation, not so much for the initial part, which is normally going to be done with photons because you want to make sure that you hit a lot of the area under the breast in order to be, or what remains of the chest wall. But a lot of times the scar incision will need to be irradiated in order to make sure there's no lasting tumor within that scar area. Administering boost dose to nodes. It used to be, if you can believe this, that you could treat a head and neck with a yoke field. You would have an upper part in order to be able to hit certain parts of the head and neck. And then in order to spare the cord, you'd just have electron strips in the back. And the reason is that you didn't have the electron beam reaching the spinal cord in the back. Now, with IMRT and whatnot, it's kind of a lost art, but yes, that used to be done. There's different types of electron interactions. You've got elastic and inelastic collisions here. Here, energy is conserved with elastic. Inelastic energy is not conserved. Within these two different types, you've got collisions with nuclei and atomic electrons. In both cases, when it comes to inelastic collisions, you're looking at Bremsstrahlung. When it comes to atomic electrons with inelastic collisions, you're looking at ionization and excitation. Obviously, it's these kinds of things here that we're definitely interested in as far as the electron imparting dose within the body. So in low atomic number or low Z materials, electrons are going to lose energy mostly through ionizing events with atomic electrons. In the higher atomic numbers like lead, Bremsstrahlung production is more important. So that's the difference between those two types of interactions. A secondary electron, so in the collision process with the atomic electrons, if the kinetic energy acquired by the stripped electrons is large enough for it to cause further ionization, then you've got yourself a secondary electron. Collisional losses. You've got ionization and excitation. You've got rate of energy loss is going to depend on the electron density of the medium. The rate of energy loss per gram per cubic, or not cubic, but square centimeter. This is going to be the mass stopping power. Remember all of that stuff that we had regarding the attenuation coefficients and whatnot? This is where that starts to come into play. So the rate of energy loss per gram per square centimeter, or the mass stopping power, is greater for low atomic number of materials than for high Z materials. Reasons for that: high Z materials have fewer electrons per gram than low Z materials. High Z materials have more tightly bound electrons, which are not as available for this type of interaction. They want to hold on to those electrons. They don't want to let them go. And they're more powerful. They can do that kind of thing. The energy loss rate first decreases and then increases with the increase in electron energy, with a minimum occurring at 1 MeV. The electron loss rate of megavoltage electrons in water is roughly 2 MeV per centimeter. Now that's collisional losses. Radiation losses, you're looking at Bremsstrahlung, or the rate of energy loss per centimeter is approximately proportional to the electron energy and to the square of the atomic number. Probability of radiation loss relative to the collisional loss increases with the electron's kinetic energy and with the atomic number. The X-ray production is more efficient for high energy electrons and high atomic number absorbers. So here's kind of what they were talking about here. When you're looking at the rate of energy losses, when you're looking at collisional, it decreases to a particular point, and then it hits a minimum around 1 MeV, which is the electron energy, and you can see the energy loss over here. So it hits its minimum here with both water and lead at this particular point, and then it increases as it goes along. And so you're looking at about 2 MeV per centimeter, so it's being lost. For radiative losses, again, we are looking for collision, or its increases with the electron kinetic energy and with Z, which is exactly what we're seeing here. And it's approximately proportional to the electron energy and to the square of the atomic number. So with electron interactions, the rate of energy loss, or the polarization or density effect, you're looking at here the value here for gas is going to be greater than the value here for a dense medium. So because of the polarization of the condensed medium, atoms close to the incident electron track screen those remote from the track. The ratio of water to air varies with energy. Therefore, the conversion from dose to air to dose to water is going to vary with depth. And that's one of the things we talked about in chapter 8. And because electron energy decreases with depth by 2 MeV per centimeter in water, and that will come back again. So unrestricted stopping power refers to the energy lost by a charged particle to the medium. Restricted stopping power, the linear energy transfer, refers to the energy absorbed by the medium. Collisions in which the energy loss is less than delta. So here you can see the energy being greater than delta, carried away by the delta ray. So when an electron pencil beam passes through a medium, it's going to suffer multiple scattering, resulting in the spread in both lateral position and direction. This is what you're seeing here. Comes in, bing, and then starts to scatter. This spread is approximately Gaussian, in other words, bell-shaped, the bell curve, if you've seen that. The mass angular scattering power is going to be theta squared divided by the density times the length. This is going to be the mean square scattering angle. That's probably a lot of gibberish for you, but it basically, we're boiling it down to saying high Z materials are used for electron scattering foil to spread out the electron beam. And recall that the photon beam is spread out by the production of Bremsstrahlung itself. All right, so what do we have here? We've got our phantom, we've got our accelerator, and at the exit window here coming through, it's fairly monoenergetic. All right, so it comes through, boom, boom, hits the filters, and the electron beam comes in and strikes the phantom. So at a particular depth, Z, further energy degradation and spread is what is going to take place. And at the surface, the energy degraded and spread due to the collision with the scattering foil as well as the air. So we've got energy in arbitrary units. We have our fluence here in arbitrary units. We have our energy at a particular depth, and then we can see how that energy is going to change as we head towards the surface. So before we hit the window, we've got a certain amount of fluence coming through. Once it strikes at the surface, or Z is equal to 0, we can see what the fluence is, and then we can see it start to fall off. So again, the measurement is going to be the most probable energy. In other words, the mean energy and energy at a particular depth. So R sub P is going to refer to the practical range. Again, the most probable energy is E sub P. So E sub P here at 0 is going to be modeled with this particular formula, and you can see the coefficients that you would plug in here if you also know the practical range of the beam. So the mean energy at the surface, and this bar over here is what's reflecting the mean, the average. So at the surface, and so this number that's being put in here is going to be your depth. So at the surface, it's going to be 0. If you put in 0 here, what you find out is the mean energy at the surface is going to be equal to this. C4 is roughly going to be 2.33 MeV per centimeter. Energy at a particular depth is going to be written in this particular form, and if you are looking for the average of each, then you replace or put a bar here for each one of those in order to be able to produce the average. So, calibration. The ion chamber, you've got plane parallel for electron beams with energies less than 10 MeV, and either plane parallel or cylindrical chambers for higher energy beams. The phantom water is going to be the preferred medium. Pretty easy to get a hold of. You can pump it in, and to most clinics will have water tanks and whatnot. Very easy to be able to calibrate your machine with. It needs to be large enough to provide full scatter for all field sizes and energies. The reference depth and field size, the point of maximum dose on the central axis. The chamber should be positioned in the deepest part of the maximum in order to avoid low energy electron contamination problems. 10 by 10 field size or cone, dose per MU at the depth of D max is set at 1 centigrade per MU. Output calibration. The chamber voltage should be arranged to give less than 1% loss in charge by ion recombination. The chamber polarity, difference between the charges measured at positive and negative polarizing potential should be less than 0.5%. The perturbation and replacement correction, so corrections based on experimental data, comparing responses of cylindrical and plane parallel chambers to electron beams of various energies. And you've got displacement correction. So the displacement correction of 0.5 times the radius of the chamber for all energy electrons and depth. So if you remember the discussion regarding absolute and relative dose, absolute dose can be measured with an ionization chamber or calorimetry or a Frick dosimeter. Relative dose can be measured with film, TLDs, or diodes. In most cases, at least in our clinic, we would prefer diodes, but film is something that we have come to learn to deal with. It's going to be customized a little bit more. Each one has its advantage and disadvantages. Film will allow us to be able to cut whatever size that we need in order to be able to place so that we know what the reading is. A lot of physicians will ask for the beam to be measured, and these are the ways that you do that. They want to make sure that the amount of dose that is being put into the patient is accurate. They want to make sure that you're spot on. So the only way to do that is to put something in that particular field that doesn't obviously disturb it too much, but gives you an accurate reading as far as what you're putting in. And these are the techniques that will be used. And these are the kinds of things that you might be doing clinically. It's helping to place those, or you might see the physicists come in and place those. The determination of absorbed dose. So the depth dose distribution, you can see them over here. You've got your 6 MeV chamber. You've got the 22 coming out over this way. If an ion chamber is used to measure the electron beam depth dose, the conversion from depth ionization to depth dose involves the water to air stopping power ratio, which is depth dependent. That's a mouthful. In addition, if the chamber is cylindrical, the measured depth dose curve needs to be shifted to account for the effective point of measurement. If a diode is used, the diode response is taken as the depth dose and no correction is needed. So, energy independence for electron relative dose measurement. The optical density can be taken as proportional to dose without correction. For film dosimetry here, you can see some of the readings, and you would see what with film dosimetry, whatever these depths happen to be. Hopefully you wouldn't be that deep into the patient, I would think. So you can see the picture. Remember that I was talking about the bowing that goes on with these particular types of beams? That's exactly what you're seeing here with this description of isodose lines. In other words, the 100% isodose line, what you're seeing there is whatever your prescription would happen to be. If you're prescribed to the 100% line, you want to deliver a certain amount of dose to that particular line. This would be 95%. A lot of times you won't prescribe to the 100% line. A lot of times you will say, well, I want to deliver, say, 30 gray to the 95% line or to the 90% line. That means that this line, whatever lies on that line, is going to be getting that particular dose. So if you prescribe 30 gray to the 90% isodose line, any point lying on that line is going to be getting 30 gray. That's the goal. So if you are having air gaps that are adjacent to the film, you can have some pretty messed up readings here. These are the kinds of things that you want to avoid. If you have film sticking out of the phantom, you can have some changes here as well. If you have a film recess inside the phantom, you can see some things such as this. Placement of the film is going to be very critical. Water is considered the standard phantom. Water equivalent plastic phantom. Solid water is one of the things that you might call it. A polystyrene electron solid water. It has the same electron density, has the same effective Z, has the same, therefore, has the same linear stopping power, S, and the same linear angular stopping power. It's much easier to work with. That's why a lot of physicists will have that in order to be able to do their measurements. It's much easier to work with than a tank of water. Depth dose measured in plastic phantom converted to depth dose in water. You can see here how all of these factors are being put together. So you've got the depth dose, or the dose measured at a particular depth in water is going to be equal to some depth that is in the medium, and whatever the dose happens to be with that, multiplied by a stopping power ratio, as well as our fluence. You can see here, there is another ratio here. So the dose in the water is equal to the dose in the medium with the R50s of water over the medium. Here are some values that go along with that. So what are the characteristics of a clinical electron beam? The major attraction of the electron beam is the shape of the depth dose curve. In the 4 to 15 MeV range, the region of more or less uniform dose is followed by a rapid drop off of dose. So the buildup is not as prominent as with photons. That if you're looking for something superficial, that is a distinct advantage over photons. Now, the more you pump up that dose, or the more you pump up the energy of the electron beam, you're going to lose that advantage. So high energy electrons lose energy or range at the rate of about 2 MeV per centimeter of soft tissue or water. Beyond the maximum range of electrons, the dose is contributed only by X-ray contamination of the beam. The tail of the isodose distribution, which is bremsstrahlung radiation. So the depth dose distribution is determined by 3 different methods: ion chambers, diodes, or film. Ion chambers, corrections are made for change in stopping power ratio of water to air with depth. Silicon diodes, they're a small size, they have high sensitivity, but suffer from energy and temperature dependence and can be damaged by radiation. This is what leads us to film. It is convenient and a rapid method. Depending on the calibration curve that you have, you can get your results back somewhat quickly. It's not as quick as, perhaps having a portal QA or something like that and having your results back almost immediately after you shoot it. So there is a little time there, but it's still worth it as a secondary check to make sure that whatever dose you have delivered is in fact what you're measuring. So for film, the depth dose distributions measured by film agree well with those measured by ion chambers. So that's good. Cannot be used reliably and absolutely because the optical density of film exposed to electrons depends on the emulsion, processing conditions, and magnitude of absorbed dose. So in other words, you got a lot of factors going on there. So the central axis depth dose curves, the region of 1 of a more or less uniform dose followed by a rapid fall off of dose, and it tends to disappear with increasing energy. That's generally what you're looking for electron beams, even photon beams. You want to be able to hit an area with a homogeneous amount of dose and then watch it disappear or fall off as you're outside that particular volume or area. So the depth in centimeters at which electrons deliver a dose of 80 to 90 of the 80 to 90 isodose level is about 1/3 to 1/4 of the electron energy in MeV. The most useful treatment depth is given by the depth of the 90% depth dose. A lot of physicians are going to end up prescribing to the 90% line, just simply because it is going to encompass a bigger area than, say, the 100% line. But at the same time, you're not going that far deep. You're not going down to an 80% line or something like that, in which you're covering way more material. So that's the difference here. If you're looking for 90%, you're looking at somewhere around 1/4. If you're wanting to translate that into a distance for 80%, you're looking at E divided by 3. The skin sparing effect is modest or non-existent, depending on which energy you're going with. And the percent surface dose for electrons increases with energy. And at lower energies, electrons are scattered more easily and through larger angles. You may end up having some physicians say that 6 MeV is a little bit squirrely. It's not really doesn't have as much of a predictable effect, quote unquote. So some physicians will choose, rather than to use a 6 MeV, they might use a 9 MeV with bolus in order to be able to get more of the effect that they're depending on. Isodose curves. Scattering of electrons help to determine the shape of the isodose curves. The collimation system and the air column above the patient cause an angular dispersion of the beam, as well as the energy spread. Individual spread of the isodose curves vary depending on the isodose level, energy, field size, and collimation. Higher isodose levels tend to show lateral constriction, which becomes worse with decreasing field size. All right, so we got a 13 MeV beam. You've got the useful region here, so you've got your range going up to, if you take 1/4 of that, you're looking at, let's see, not somewhere around 3.25. So you're looking at a useful range right in with here. You're looking at obviously the D max looks like it's right about in there, which for 13 seems to be about right. And then you can see the sharp fall off here. So you've got the depth of the 80% line right here is about 1/3 of this particular value. So you're looking at about 4 1/3, which in water, that's about what you're looking at right there. You've got the practical range, the range at which you're going to be able to hit most of your targets is right about there. And then you finally have some of the Bremsstrahlung tail, which still exists out there, but it's not contributing that much to the beam. So the Dmax is going to increase with energy for low electron energies, and it's approximately 2.5 cm for high energy electrons between 12 and 20. This is going to be the area of relatively uniform dose. That's what you're going to be using for treating. The modest skin sparing is going to increase, or the skin sparing, I don't know why it says with increasing energy, I think is increasing skin dose. I think is the way to look at that. Your lower energies there will spare the skin a little bit more. You've got all of these tails after you that are on these particular lines that come here after the R90 and the R80 are hit. These, of course, will increase with energy because they're directly proportional to that. Roughly here, you're looking at R90 being divided by 4, R80 being divided by 3. So the choice of the beam energy is much more critical for electrons than photons. Yeah, I suppose that's true. The depth there for those electrons and how far they can penetrate will let you know exactly how much of a superficial lesion that you're going to be, or how deep you're going to be able to treat. So you do need to choose wisely. Okay. So lower electron energies, lower energy electrons scatter more and through larger angles, causing more rapid buildup. Thus, the difference between the surface dose and the maximum dose is going to end up being larger. Higher energy electrons scatter less and through smaller angles, causing less rapid buildup. So if there is no scatter, there will be no buildup. So here you have a comparison of central axis depth dose distributions. You've got the PDDs here for 7, 9, 11, 15, 18, 25, God forbid, 35. You've got, and you can see how deep these go. I mean, 20, if you're looking at 18 centimeters below the surface, some patients don't have a separation much more than 24. So you can be going straight through with some of these patients here, at least as far as some of the exit dose for electrons, which is rough to think about. But you'll see a lot of these energies down here used in the clinic quite a bit. Now, for 7 MeV isodose curve, for different machines, you're going to have different collimation systems, and that's going to mean a different dose distribution. So for low energy electron beams, isodose curves are going to bulge out for all dose levels. You will see some bulging here at the 18, but what do you notice? You notice a larger bulge here at a shorter distance in. Here you can see the 18 is actually pushing through quite a bit. Now you'll still see some bulges here, but they're nowhere as near pronounced as they are over here. Now the flatness of an electron beam should be specified in a reference plane perpendicular to the central axis at a depth of the 95% isodose line beyond the depth of dose maximum. Variation in dose relative to the dose at the central axis should not exceed plus or minus 5% over an area confined with lines 2 centimeters inside the geometric edge of fields equal to or larger than 10 by 10. You compare dose profiles on one side of the central axis to that of the other. Hopefully they would be very much the same. Crossbeam profile in the reference plan should not differ more than 2% at any other points or pair of points located symmetrically on the opposite side of the central axis. You want to be able to produce an electron beam that is homogeneous in many different characteristics. It's flat on one side as it is the other, because you don't want to have to try to line a patient's up, maybe with the right side of the beam as opposed to the left side of the beam. That's not really what you're looking for. You're looking to have a nice flat beam that's going to interact with the patient. So flatness, field flatness and symmetry. You've got a uniform index where you've got the A of 90% and then the A of the geometric edge, or a uniform index of the 90% over the 50%. And you want that greater than 0.7 on a reference plane at a reference depth. D max is less than 103% of D along central axis. And then you've got the symmetry here where you're measuring plus or minus on either side. Got your charges here and divided by the average, and you want that difference to be less than 2%. So how are the beams collimated? You've got dual foil collimation, where the first foil widens the beam by multiple scattering, and the second foil is designed to make the beam uniform in cross-section. It's designed to provide a variety of field sizes and to maintain or improve the flatness of the beam. So you've got the dual scattering foil system here inside the head of the gantry. Collimator jaws are going to open to a fixed predetermined size for a given electron energy and applicator size. These are usually set by the manufacturer, so it's not something you really want to mess around with. So the variation of the output with the collimator jaw settings. So you can see the relative dose compared to the energy over here. Output increases smoothly with field size as defined by the insert with collimator jaw size fixed. So you can see the side of the square field and the output factor. Here you can see a large field size with PDD nearly constant. Small field sizes, the PDD increases significantly with the field size. So the PDD increases with field size until it exceeds the lateral range of the electrons. Then the PDD is almost constant with field size. So the output and the PDD for small field electron beams needs to be individually measured. So for large fields, the PDD are nearly the same and thus are equivalent. For small circular fields, the equivalent field radius to a 2x2 square field is roughly equivalent to this. For small rectangular fields, as discussed, as a result of the Gaussian pencil beam distribution, the PDD is related to that of the square fields by this. Most of the time, the physicist is going to measure these particular blocks, and they're going to come through and they're going to give you or give the dosimetrist the monitor units in order to deliver a set amount of dose. And when they do that, a lot of this kind of stuff is taken into consideration. Pencil beam or pencil electron beam, after passing through the vacuum window of the accelerator bending magnet, scattering foils, monitor chambers in the intervening air column is spread into a broad beam that appears to diverge from a point. The virtual source is going to be defined as an intersection point of the back projections along most of the most probable directions of electron motion at the patient's surface. So in other words, they don't really have a point source. They are considered to be virtual. So you've got the accelerator window, you've got the beams that's starting to spread out here. If you were to back project those, this would be where your virtual SSD or your virtual source would most likely be located. You can see several equations here in order to be able to determine if you have a gap. And then for this particular value, then you can figure out these particular relationships over here. X-ray contamination, determined from the tail of the depth dose curve by reading off the dose value at the point where the tail becomes straight. So contributed by Bremsstrahlung interactions of electrons with the collimation system and the body tissues. So you can see that that's what's going on in this particular tail. Dose due to X-ray contamination generated in the collimation system and the phantom. So you can see the higher you go here, the more contamination you're going to have. And dose due to X-ray contamination generally is not a concern, except for total skin electron therapy, in which the entire body is going to be irradiated. And the X-ray contamination dose is increased sixfold. Again, when it comes to treatment planning, the choice of the beam energy is going to be dictated by the depth of the prescription level, typically somewhere between 80 to 90%. The choice of field size depends on the construction of the isodose curve of the dose level. The margin between 90% and geometric field edge typically is greater than half a cm. So you're going to be looking at the depth of the target volume, the minimum target dose, the acceptable dose to critical organs. You're going to set it such that the target volume lies entirely within the 90% isodose curve. The higher the isodose line that you prescribe by, the more tightly you can control the dose you want delivered. That's based on the isodose coverage of the target volume. Larger field at the surface than usually used with photon beams may be necessary to cover a target area adequately. Most times, these electron apertures are set clinically, which means patients brought in, sat down at the accelerator, and they figure out exactly how to draw this aperture there clinically in the room. Normally, that's going to be done at the accelerator. A lot of times you can't have that done at the CT unit, and sometimes doctors will take CTs of a patient in order to be able to figure out exactly which energy they might want to use, because they, on the surface, you may not know how deep this cancer runs. So here we are looking at corrections for air gaps and beam obliquity. We are looking at a curved surface here. So what we're wanting to do, say on a leg, is perhaps we are looking at something that maybe needs to be built up or has a curve to it that needs to be corrected for, which is kind of what you're seeing here. If we were to hit this particular part with a beam that is straight on, it's going to get far less dose than what we would be seeing over here. And the Dmax shift towards the surface with increasing incident angle. And it's decreased penetration with increasing angle. So there are a number of reasons here why you might want to start to take a look and see, well, maybe we can start to build up, correcting for air gaps, or maybe have a more straight surface in which this can be delivered. So the effect here is that this would be a normal curve. If you had an electron beam here, here, and here, you can start to see how these things bow out. You can start to see how much dose is delivered here. However, let's say you take that surface, and rather than have it be a straight perpendicular to the electron beam, so you put it at an angle, you can see here some depths are going to get more electron dose than the others. You're going to see increased dose at shallow depths due to the greater side scattering. Decreased dose at larger depth due to the lack of side scatter, since it is beyond the range of the network pencil beams. So you can see a representation of irradiation of the chest wall with sloping surface dose. So you can see that with a slope there, it's going to start to affect how much is actually going to be irradiated. This actually, a surface contour, you could take a piece of wire or something over a patient, and you can actually go through without using a planning system and go through and figure out exactly how much dose you need to deliver. Nobody does that anymore, but it can be done. Surface irregularities. They produce local hot and cold spots, and the electrons are scattered outward by steep projections and inward by steep depressions. And sharp edges may be smoothed with a certain bolus. That's actually, those can be some really neat projects. So let's say you've got the air here, you've got some water here, you've got low dose areas over here due to the loss of scatter. You've got high dose here due to extra scatter. In other words, you don't have anything coming in here, so you've got a little bit of loss of scatter in these particular spots because you don't have that interaction going on here. But whenever it does hit, you can have a little bit of extra dose here that maybe you weren't counting on. If you go and you plug that with some sort of water or whatnot, and you have the dose come in, and let's say you plug it a little bit too much, you can have areas here that have extra scatter, and you can have some low dose areas over in this particular spot where the electrons are no longer able to make it through that. So electron beam dose distribution can be altered by tissue inhomogeneities. I mean, people are not phantoms. So we're going to have different densities for different types of tissue as we go through. Because those differences exist, you're going to be looking at enhanced scattering effects. So the CET, or the coefficient of equivalent thickness, is going to be used to correct those dose distributions. So you've got an approximation of that where you're coming up with an effective dose. So you're trying to figure out exactly how far these beams are actually penetrating. So you can see here, if God forbid you ever try to use an electron to try to treat something in the lung, you don't really want to do that. But as for tissue inhomogeneity examples, if you have tissue coming in, and let's say you have a lung inhomogeneity, you can see that the beam is actually going to be headed out further than what it would as if it were solid. And that's the kind of thing that is going on here. So we do try to correct for those types of inhomogeneities. So let's say you've got a material M prime that has greater scattering power than material M. These are the kinds of dose distributions that you might have going on. You might have a hot spot over here, and you would have a cold spot here because all of this material is blocking the electrons coming in. So the idea of bolus, that when you're putting it on a patient, is to flatten out an irregular surface, trying to make it a little bit more even. It will reduce the penetration of the electrons in parts of the field, and it will increase the surface dose, as you might imagine. Equivalent to tissue in stopping power and scattering power. You're looking at materials like paraffin, polystyrene, lucite, super stuff, and superflab. This is the thing that I see most in our clinic. Although you can make up some blue bolus, depending on what surfaces you might need it for. By the time the physicist finishes, it looks like they murdered a Smurf there in the room. You've also got a plate of low atomic material such as lucite and polystyrene, and sometimes used to reduce the energy of the electron beam. So a bolus is going to be used to flatten out an irregular surface. It'll reduce penetration in parts of the field, and it'll increase the surface dose. So As I was remarking before, adjacent fields, let's say you've got two adjacent electron fields that are overlapping or abutting, that's going to cause a danger of delivering excessively high doses in that junction region. Hotspots can be accepted depending on their magnitude and extent and location. One of the areas where I have seen that used is when you have an IM field that is going to be treating nodes that are next to the sternum that are in junction with photon fields that are going to be hitting a patient's breast or chest wall. When you junction or you match that electron field with the photon field, you're going to have bowing from that electron field enter into bowing from the electron field entering into the photon field. When that happens, you can have some pretty significant hotspots come on depending on what the geometry is, and that can be problematic when it comes to planning, and it can be horrific when you are the patient receiving it. So you can see here, you've got, if you have a gap in between fields, you'll have a cold spot. If you try to close that particular gap, this is what starts to occur. And then if you make that gap even smaller or whatnot, you can have some pretty big increases in the heterogeneity of the dose. Here's an example of a 9 MeV and a 6 MV. You can see the bowing effect start to happen right here. With increased SSD, it leads to a wider electron beam penumbra, resulting in larger areas, in this case, of a hotspot. Not something you want. One way to try to help minimize bad effects in the patient is by using external shielding. So the electron beam can be shaped by cutouts made of cerebin or lead, and they're placed in an applicator or a cone or directly on the skin. Shielding too thin, an eye shield can cause dose buildup at depth immediately under the shield. Very, very bad. Shielding thickness to achieve a transmission of less than 5%. If you have that amount of lead there, then you can really dampen down, and you certainly wouldn't run into incidences like this. So you can see here the shielding thickness and the electron energy, and you can see the positive correlation here. So as this goes up, this should go up. So lead thickness in millimeters is required to stop primary electrons transmitted dose due to bremsstrahlung photons generated in the shield. For cerebin, since it operates a little bit differently from lead, you increase the thickness by 20%. This actually came out of the summary, that lead thickness. You can see the effect of blocking here on the dose rate. So the block field is less than the electron lateral range. So when in doubt, individual dosimetry, output depth dose isodose distribution should be made for irregularly shaped cutouts. So if you got, say, protection of the eye in the treatment of the eyelid, you can see that the electron backscatter, and you can see the energy in MEV. So you can see you got a lot of backscatter going on with these lower energies. That dose enhancement at the interface due to the extra backscatter from the lead is going to be D prime divided by D. That's not good, and you need to take care of that. Depth dose curve without lead in the polystyrene phantom. That lead thickness required to stop primary electrons is roughly MeV divided by 2. For cerebin, you increase it again by 20%. So a thin layer of low Z material like wax, which is pretty malleable, can be placed in front of the lead shield to reduce the backscatter. So the depth in polystyrene upstream from the interface. So you can kind of see the backscatter intensity with the depth. So let's say you've got some sort of oral structure here. You've got a piece of aluminum and lead shield, and then you've got the cheek here. So immediately beyond the cheek, you've got 9 MeV minus 2 MeV per. You've got effectively here a 5 MeV. So to protect the oral structure, the lead thickness needs to be roughly 5 MeV divided by 2, or 2.5 MeV. So what you're wanting to do is you're wanting to hit the cheek. You know that right beyond the cheek, you have the 9 MeV over here. Beyond the cheek, you've got 5 MeV. You don't want that going, say, into the oral cavity or what have you. So that's why you put in the lead shield and the aluminum. But how much do you need? That's where the backscatter, or that's where the lead thickness is calculated from. How much backscatter are you going to have for a 5 MeV? Looks like it's about 56%. The depth upstream from the interface to reach 10% of the dose is going to be 10 millimeters in polystyrene, or about 4 millimeters of aluminum. These are the electron arcs that we were talking about. This is suitable for treating superficial tumors along curved surfaces. I have never actually planned one of these myself, but you can see the dose is increased at larger depth and it's decreased at the shallow depth. So the effect depends on the field width and arc size, and the range of angles at a given point is irradiated. It has nothing to do with the rotation speed. So the greater or a smaller field width leads to lower dose rate, which leads to greater X-ray contamination. Smaller field width, normal incidence at all angles, and typically a field is going to be 4 to 8 centimeters at the isocenter. The location of the isocenter is approximately equidistant from the contour surfaces of all angles, and the depth of the isocenter is greater than the electron range, so that dose from primary electrons is not accumulated. You should see some gradual dose fall off at both ends of the arc. Use surface shield to better define the dose distribution. Say if you don't want the dose coming in at this particular area, you put in the lead strip and that will stop it. Total skin irradiation, you're looking at 2 to 9 MeV electron beams are going to be useful in treating superficial lesions covering a large area of the body. You've got the Stanford Technique, in which you have the patient positioned in several different ways. You've got a calibration point, you've got the beam center line, and you've got how much you want to expose the patients. You make all of these particular measurements. So if you have an arc field versus a stationary field, you'll end up seeing a little bit of a difference here in terms of the projected dosimetric field and the relative dose penetration. You can see along here, you'll have X-ray contamination along the beam's central axis. And to reduce the X-ray contamination, you angle the central axis away from the patient. You're looking roughly at around 15 degrees above and below, and you'll have the certain first day treatments. Here you have the anterior of the patient, then hit them from the posterior, and then the second day you'll hit them for 2 angles from the anterior and then 1 from the posterior. The depth dose curve and the Dmax shift towards the surface due to oblique incident angles. You've got, with that 6-field technique, the dose uniformity of plus or minus 10% can be achieved in general, except in areas with large surface irregularities like an inner thigh, where supplementary irradiation may be needed. And Bremster lung dose in patient midline is approximately doubled due to the opposed beam arrangement. But trust me, if you're going through all of this and you end up with a uniformity of 10 plus or minus 10%, you're doing pretty good. You can place films here in order to be able, you've got usually a plastic screen. I have done this once, a grand total of once. You've got a distance here of about 400 cm, and you're going to need that in order to be able to cover the entire body. You've got films here. You've got a plastic screen here in order to be able to, I believe it's helped to disperse those electrons. And you've got films here in the way, so you can make measurements. And then you can see the relative dose given the distance that is transversed. It's a pretty involved operation here. You've got a modified Stanford technique in which you have a single dual angle field. You've got a parallel plate chamber in order to be able to measure that. Again, I would be very surprised if you end up in an area where you'd be doing this. You've got a dual angle field here. You've got all 6 fields if you're wanting to measure this using a piece of film. And then although an overall surface dose uniformity of plus or minus 10% can be achieved, again, there are the localized regions of extreme non-uniformity. And TLDs are most often used for in vivo dosimetry. The pencil beam is based on the multiple scattering theory. You have a distribution based on the normal distribution of how these things are scattered. And you have dose due to an infinite field size beam here in part of your computations. That follows the bell curve. I'm not exactly sure how much we really need to get into this at this particular level, because this, while the pencil beam theory or algorithm was something that was used before, it has again been superseded by other theories. However, it's good to know. I would not ask you to be able to do that on an exam. If you have more questions about that, I suppose we can go into this a little bit more. Again, this is the most important part out of this. For more accurate electron beam dose calculation, Monte Carlo methods are available in the modern day planning systems. So that is an exposure here to, pardon the pun, for electron beam therapy. So hopefully you took a few of the major points out of this.